Welcome to Lecture 10. This week I'm going to be talking about inner product spaces, orthogonality, and orthogonal sets and orthonormal sets. First, let's talk about inner product spaces. Last semester in Mathematics 2, we studied the dot product of two vectors in R2 or in R3. Let me very quickly remind you that if we're in R3 and if we have vectors u and v, the dot product of u and v is u1 v1 plus u2 v2 plus u3 v3. And if we do the dot product of a vector with itself, then we get the norm or the length of u squared. In today's lesson, I want to extend the idea of a dot product to real vector spaces. Last week we were talking about complex vector spaces. I don't want to deal with those issues this week. So this week we'll restrict ourselves to real vector spaces. If you have to do something like this in a more advanced course, then you may have to do complex vector spaces. And the idea is the same, but with a little bit of extra complication here or there, which I'll point out. So this week, anytime you see a number or a scalar k, then you can assume that it's a real number. This week, we don't need to worry about complex numbers. An inner product on a real vector space V is a function, and it's a function which takes two vectors and it gives us a real number. And this function must satisfy four rules or four axioms. View v and w are vectors, and if k is a number. Rule number one says that the inner product of u and v must be the same as the inner product of v and u. We can always swap our vectors around and it doesn't make a change. That's not true in complex numbers, but we're not worrying about that. If we have two vectors added together in the first position, we can always cut there. We can always imagine just taking a pair of scissors and cutting at the plus, and we can cut this into two different inner products. The inner product of u and w plus the inner product of v and w. Rule number 3. If we have a number k in the first position, if the first position is ku, we can always take that number outside of the inner product. If we put 2 and 3 together, that means that our function is a linear function in the first position. So for whichever vector we put in the first position, that means we have a linear function there. And rule number 4 is that the inner product of a vector v with itself, v inner product v, is always greater than or equal to 0. And the only way that we can have inner product of v with itself equal to the number 0 is if v is the 0 vector. So if v is not the 0 vector, the inner product of v and v is always strictly greater than 0. Now, if we used Rule 1 and Rule 2, Rule 1 says we can swap the positions of u and v, and Rule 2 says if we have a plus in the first position, we can cut there. If we combine them together, then we can see that the inner product of u and v plus w swap their positions, first of all, using Rule number 1, and then cut at the plus, and then swap positions again. We get uv, inner product of u and v, plus inner product of u and w. So actually, if we have a plus sign in the second position, we can also cut at the second position. Likewise, if we use rules 1 and 3, it's possible to prove that if we have a number k in the second position, we're allowed to take that outside. I'm not going to prove that. You can write down a proof of this just using rule 1 and rule 3. And we could also prove, and again I'm not doing this, that if one of the vectors is the 0 vector, for example, inner product of the 0 vector and v, or inner product of v and the 0 vector, then we always get the number 0. This is a typo here. This should be the number 0. For example, let v be r to the power n, and define a function like this. A function of u and v is going to be u dot v. So in other words, it's going to be u1 v1 plus u2 v2 plus, and then keep going because we've got n coordinates, and finish at un vn. This I'm claiming this function is an inner product on Rn, but I'm going to leave that for you to prove. You need to prove that all 4 axioms are satisfied for this function. This inner product, this dot product, is called the Euclidean inner product on Rn. If we have a vector space together with an inner product, then it's called an inner product space. That's all it means. Inner product space just means a vector space together with an inner product. So for example, Rn together with this dot product or this Euclidean inner product is an inner product space. If V is an inner product space, then we can define the norm of a vector, or the length of a vector, which we write as 2 vertical lines v, 2 vertical lines, using this formula. Norm of v is defined to be the square root of the inner product of v comma v. Remember, inner product of v comma v is always non-negative. It's always greater than 0 or equal to 0. And we're allowed to take the square root of a non-negative number. And just as we talked about last semester, a vector of norm 1 is called a unit vector. So in other words, a unit vector is some vector u which satisfies that if we take the norm of u, we get the number 1. The first theorem for today's lesson. If u and v are vectors in an inner product space V, if k is a scalar, then the norm of v is always greater than or equal to 0. The only way that the norm of v can be equal to 0 is if we have the 0 vector, and the norm of the 0 vector is always 0. And thirdly, the norm of k multiplied by v, number multiplied by vector, is the absolute value of k multiplied by the norm of v. V is a vector. For vector, we use 2 vertical lines. K is a number. For number, we use 1 vertical line on each side. I'm going to give a partial proof. I'm not going to do all the details. Why is number 1 true? Norm means square root of the inner product of v with v. Inner product of v with v is always a positive number. Take the square root of a positive number, we always get a positive number. So that's the proof of 1. Proof of 2, again, using the formula in the yellow box. The norm of v is equal to 0 if and only if the inner product of v with v is 0. But by definition, that's true if only if v is the 0 vector. And number 3, norm of kv squared means inner product of kv with kv. K in the first position, we can take it out. K in the second position, we can also take it out. So we have k squared outside inner product of v with v, or k squared norm of v squared, and that's it. If V is an inner product space, then we can define the distance between two vectors to be the norm of U minus V. Let's look at a different example of an inner product. Let U and V be vectors in R2 and define a function of U and V to be 3U1 V1 plus 2U2 V2. Show that this function is an inner product of R2. To answer this question, we need to show that all four of the axioms are true. So let's go through them. The first axiom said that we must always have that the inner product of U and V is the same as the inner product of V and U. We look at the formula. If we swap U and V, then nothing changes. 3U1 V1 is the same as 3V1 U1, and 3U2 V2 is the same as 2U2 V2 is the same as 2V2 U2. So rule number 1 must be true. Rule number 2, I've written a partial proof here. Start with U plus V comma W, inner product of U plus V and W. Write it out. Keep playing with it, and you can end up with inner product of U and W plus inner product of V and W. I'll leave that one for you to finish. You fill in the details here. Rule number 3 is the same. Just using the rule, and then take your K outside. We just end up with K multiplied by the inner product of U and V. So that just leaves rule number 4. An inner product must always be greater than or equal to 0, and the only way it can be 0 is if we have the 0 vector. But what is the inner product of V with V? It's 3V1 squared plus 2V2 squared. That must be positive. V1 squared must be positive. V2 squared must be positive. And how could we get equal to 0 here? The only way we could get equal to 0 here is if both V1 and V2 are equal to 0. So rule number 4 is also true. That proves that this function is an inner product. And actually, this function is called a weighted Euclidean inner product. The numbers 3 and 2 in the definition here are called weights. We can do some calculations with weighted Euclidean inner products. Let U be the vector 1, 0 in R2. If we use the Euclidean inner product, then the norm of U is 1. So if we use the Euclidean inner product, then U is a unit vector. But if we use the weighted Euclidean inner product from the last example, then the norm of U is the square root of 3. So if we use the weighted Euclidean inner product, then U is not a unit vector. Unit circles and unit spheres. If V is an inner product space, then the set of all points that satisfy the norm of U equal to 1 is called the unit circle or the unit sphere in V. So this just means the set of all unit vectors in an inner product space. And that will depend on which inner product you're using. For example, sketch the unit circle in R2 using the Euclidean inner product, that's just a dot product. And then part 2, sketch the unit circle in R2 using the weighted Euclidean inner product given by this formula. Same idea as before, but we have different weights. Here the weights are 1/9 and 1/4. Okay, so for part 1, we're trying to find all of the unit vectors. So we're trying to find all of the vectors u which have norm of u equal to 1. And it's going to be easier for me if I square this. So I want norm of u squared equal to 1. So that's a vector xy dot a vector xy, or x squared plus y squared. All of the unit vectors satisfy x squared plus y squared is equal to 1. Now let's move on to number 2. Again, we're trying to find all of the unit vectors. So I'm starting with 1 is equal to norm of u squared. Y squared, just because it makes the calculation easier. So that's inner product of u and u, or 1/9 u1 u1 plus 1/4 u2 u2, which is x squared over 9 plus y squared over 4. So then draw them. In blue, I've drawn the unit circle with respect to the Euclidean inner product on R2. And in red, I've drawn the unit circle with respect to this weighted Euclidean inner product on R2. Using a different inner product gives us a different unit circle. It gives us different unit vectors. My next topic is about inner products generated by matrices. If we let A be an invertible n by n matrix, then we can define a function like this. A function of u and v, we can say is equal to au dot av, where that's the dot product on Rn. This is called the inner product generated by A. Now, let me remind you that if we're doing the dot product of two vectors, we could take the transpose of one of the vectors, move it to the left, and then multiply them together. It doesn't matter which vector you take the transposes of, as long as you put it on the left. So we could do AU transpose AV if we wanted to, but I want to do AV transpose AU. And the transpose of two matrices, you can take transpose inside the bracket as long as you change the order. AV transpose is the same as V transpose A transpose. So we could write this inner product as V transpose A U if we wanted to. And that's going to be useful on the coming slides. For example, let A be the 2 by 2 matrix, root 3, 0, 0, root 2. Straight away we can see, because this is a diagonal matrix, the eigenvalues are root 3 and root 2. 0 is not an eigenvalue, so this matrix must be invertible. The inner product on R2 generated by this matrix is actually one of the weighted Euclidean inner products that we've looked at earlier. Why? Because if we calculate the inner product of u and v, that's au dot av, or root 3 u1, root 2 u2, dot root 3 v1, root 2 v2. We just get 3u1 v2 plus 2u1 u2, which is what we saw earlier. And just let me note, if we calculated A transpose A, we get 3, 0, 0, 2. So that's just the weights on the diagonal. Let's do some more inner products. Next, I want to talk about the vector space Rn by n, or if you prefer the notation M subscript nn. That's the vector space of all n by n matrices where each entry is a real number. Let U and V be matrices in this vector space, so n by n matrices of real numbers, and then define a function like this. A function of U and V is going to be the trace of U transpose V. This defines an inner product on our n by n, and this one is called the standard inner product on our n by n. Now, it's possible to prove this by going through all 4 of the rules, all 4 axioms, proving that uv is the same as vu, inner product of u and v is the same as inner product of v and u. Prove that if we have a plus in the first position, we could cut it there. Prove that if we have a constant k in the first position, we can take that outside. And proving that the inner product of v and v is always greater than or equal to 0, and it can only be equal to 0 if we have the 0 vector, or in this case, the 0 matrix. But there's an easier way to prove this. Let's suppose our 2 matrices we write like this, U1, U2, U3, U4, etc. Then when we calculate the trace of U transpose V, I'll leave this for you to check, we get U1, V1 plus U2, V2 plus U3, V3 plus U4, V4. And that's the same as the dot product on R4. And I've already commented that the dot product on R4 is an inner product. So straight away we can say this must also be an inner product. We don't need to do the extra work. For example, if U is the matrix 1, 2, 3, 4, and V is the matrix -1, 0, 3, 2, then the inner product of U and V, I'll leave it for you to check, is 16, and the norm of U, please check, is the square root of 30. Let's move to a different vector space. Next, I want to talk about the vector space Pn. That's the n+1 degree vector space, or n+1 dimensional vector space of all polynomials of degree n or less. So let's suppose we have 2 polynomials in Pn, we call these P and Q, and then we're going to define a function, which is also actually an inner product, but I leave that for you to prove, using this formula. A0, B0 plus A1, B1 plus etc. So it's basically dot products again. I leave it for you to prove that this is an inner product on Pn. And then once we've got this inner product, we can do, oh, a typo here, there should be a square root side here. We can square root it, square root of inner product of P and P to get its norm. This inner product is called the standard inner product of Pn. Next, I want to give a different inner product on Pn. So again, I'm starting with 2 polynomials of degree n or less. And then I want to pick some numbers. I want n+1 real numbers. And then I'm going to define a function of P and Q to be P calculated at x0 multiplied by Q calculated at the point x0 plus P calculated at x1 multiplied by Q calculated at x1, and then etc. We can think of this as the dot product of these 2 vectors, the vector P at x0, P at x1, etc., with the vector Q at x0, Q at x1, etc. Is this an inner product? I'm calling it the evaluation inner product, but is it really an inner product? We need to prove the 4 axioms. The first 3 are easy. The first 3 just follow from the dot product. If they're true for the dot product, then they're also true for this. But for the 4th one, we need to do a little bit of work. We need to show that the inner product of P with itself is always greater than or equal to 0. Well, that's straightforward because we just have the square of a real number plus the square of a real number plus dot, dot, dot. That must always be positive. How can we get 0 here? The only way we can get 0 here is if P of x0 is 0, P of x1 is 0, and so on. But there's only one polynomial of degree n or less which has n plus 1 roots, and that's the 0 polynomial. Every non-zero polynomial of degree n has n roots, but we have n plus 1 roots, so we can't have non-zero, we must be 0. Time for a different vector space. Now I want to look at the vector space C square bracket A, B square bracket. That's the vector space of all continuous functions with domain closed interval from A to B. Show that the following function is an inner product on the vector space of all continuous functions with domain closed interval from A to B. Our function is defined to be the integral from A to B, f multiplied by g. We need to do the 4 axioms. We need to prove that all 4 axioms are true. First one, just play with the formula. Inner product of f and g is straightforward. We can see is the same as the inner product of g and f. Likewise, rule number 2, we'll just use the formulae and what we know about integrals. We know if we have a plus inside an integral, we can split the integral just there. So the inner product of f and plus g and h must be the same as the inner product of f and h plus the inner product of g and h. Axiom number 3, straightforward again. Why? Because if we have a number k inside an integral, we can just take it outside. So inner product of kf and g must be the same as k multiplied by the inner product of f and g. And then finally, axiom number 4. An integral of a function squared must be greater than or equal to 0. We know this from calculus. If we integrate a positive function, then our integral must always be positive. And how can we prove that it's equal to 0? Well, because it's continuous. If it's not always equal to 0, if the function has some sort of bump in it, like this, then there must be some area underneath it. If a function is positive, strictly positive at one point, then its integral must be strictly positive. Or turning that around, if we know that the integral of a positive continuous function is equal to 0, then the function must always be equal to 0. So that's all 4 axioms proved. Therefore, this is an inner product on the vector space of continuous functions. Let me show you some of the things that we can do when we're playing with inner products. Let's suppose we're starting with something like this. The inner product of u minus 2v and 3u plus 4v. Well, remember, if we have a plus in the first position and a minus sign is basically the same as plus here, we can cut it just here. We can cut this into 2. So we have an inner product of u and 3u plus 4v and a minus inner product of 3u plus 4v. But now I have a plus in the second position in each one of these. I can cut the inner product when I see a plus. So I'm going to cut each one of these into 2 and we'll end up with 4 terms. The inner product of u and 3u plus the inner product of u and 4v minus inner product of 2v and 3u. Cut at the plus, but we already have a minus, so it's minus again. Inner product of 2v and 4v. Also, Anytime we have a number inside an inner product, we can take it outside. The 3 we can take out, the 4 we can take out, this 2 and this 3 we can take out, and so on. So that's the same as 3 inner product of u and u, plus 4 inner product of u and v, minus 6 inner product of v and u, minus 8 inner product of v and v. Here's an inner product of u and v, here's an inner product of v and u, but these are the same. Turn one of them around, and then we can add 4 to minus 6. I get 3 norm of u squared minus 2 inner product of u and v minus 8 inner norm of v squared. That's the sort of thing we can do with inner products. My second topic for today's lesson is orthogonality. Two vectors u and v in an inner product space V are orthogonal if and only if their inner product is equal to the number 0. Now I want to show that orthogonality depends on the inner product. Let u be the vector 1, 1. So here it is. This is u. And let v be the vector 1 minus u. So that's this one. Note that u and v are orthogonal with respect to the Euclidean inner product or the dot product on R2 because u dot v is equal to the number 0. However, they're not orthogonal with respect to this weighted Euclidean inner product that we looked at earlier, because then the inner product of u and v is 1, which is not 0. These two matrices, u and v, are orthogonal with respect to the standard inner product on the vector space of all 2 by 2 matrices because we calculate their inner product, and please check this for me later, we get the number 0. Let P2 have this inner product. We proved that this function is an inner product on the vector space of all continuous functions. Polynomials are continuous functions, therefore this must be an inner product on P2. Let P be the polynomial x and let Q be the polynomial x squared. Are P and Q orthogonal? Let's check it. Well, we can calculate the norm of P. That's the square root of the inner product of P and P, or square root of the integral from -1 to 1 of x squared dx. That's the square root of 2 over 3. We can calculate the norm of Q. Again, it's the square root of the integral from -1 to 1 of q squared, x to the power 4, square root of 2 over 5. And we can calculate the inner product of P and Q. That's the integral from -1 to 1 of p multiplied by q, x multiplied by x squared, x cubed, but that's equal to 0. So yes, these are orthogonal vectors with respect to or relative to this inner product. Time for another theorem, a famous theorem. The Pythagorean Theorem. If u and v are orthogonal vectors in whichever inner product space you're dealing with, then the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared. Everybody learns a simplified version of this at school. But now we're doing the full one in inner product spaces. And I want to prove this theorem. Before I go on, let me just say, in my picture, I've drawn it with a 90-degree angle here. But of course, that depends on what inner product you're using. You might not always have a 90-degree angle if you're using an unusual inner product. Right, so let's prove this. And this is quite straightforward to prove. Just as I was doing at the end of the previous section, the norm of u plus v squared, that means inner product of u plus v and u plus v. There's a plus in the first position, so we can cut here and split this into two things. Inner product of u and u plus v plus inner product of v and u plus v. But then there's more pluses. We can also cut at the second place. Two things each cut into two is going to give us 4 terms. So just be careful here. If you have 2 pluses, 2 places to cut, that means 4 different terms. Inner product of u and u plus inner product of u and v plus inner product of v and u plus inner product of v and v. But wait a minute, we're assuming that u and v are orthogonal. So we're assuming that the inner product of u and v is 0. So this one is 0, this one is 0. We're just left with exactly what we want, norm of u squared plus norm of v squared. And that's it. That is the whole proof of the Pythagorean theorem. Let's go back to the previous example. We were looking at the vector space P2 with this inner product, and we had P was the polynomial or the vector x, and Q is the polynomial or the vector x squared. We've seen that these are orthogonal to each other. So by the Pythagorean theorem, we should have that the norm of p plus q squared is equal to norm of p squared plus norm of q squared. Let's check this. We've already calculated the norm of p and the norm of q. We just need to calculate the norm of p plus q and then see if this formula is true. Norm of p squared plus norm of q squared. Because we've done this already, we can see that this must be 2 over 3 plus 2 over 5, or 16 over 15. Do we get the same thing if we calculate the norm of p plus q squared? We should do by the theorem. So we want the inner product of p plus q with the inner product of p plus q, or to say it another way, we want the integral from minus 1 to 1 of x plus x squared multiplied by x plus x squared. And if you check this for me, you will see that we do actually get 16 over 50. Of course we did. The Pythagorean theorem told us that we should get 16 over 50. Let W be a subspace of an inner product space V. The orthogonal complement of W, which we write as W to the power upside down T, is all of the vectors V which are orthogonal to every vector W in capital W. Now, the orthogonal complement of W is also a subspace of V, and the intersection between W and its orthogonal complement is the set only containing the 0 vector. We can go further and say if V is a finite dimensional vector space, then the orthogonal complement of the orthogonal complement of W is equal to W. Be careful, this is only true if we have a finite dimensional vector space. Orthogonal projection. Let's suppose we've got 2 vectors, u and v, and let's suppose u is a unit vector. V can be any non-zero vector. What we can do is we can write V as the product of 2 vectors. A vector called V parallel, which points in the same direction as u, and a vector v perpendicular, which is orthogonal to u. And these are given by these formulae at the bottom. On the left, v parallel is the inner product of u and v multiplied by u. It has to be a number multiplied by u because it's pointing in the same direction as u. And then v perpendicular is given by the formula v minus inner product of u and v multiplied by u. Now, I want to show you that these are the correct formulae. First, I want to show that v perpendicular is orthogonal to u. And how do we prove that that two vectors are orthogonal? We calculate their inner product. So formulas in the yellow box at the top. I have inner product of u and v minus inner product of u and v multiplied by u. We need to simplify this and show that this is equal to 0. Well, first of all, there's a minus sign here. We can split at the minus sign. Inner product of u and v minus, I'm doing two steps at once here. After we split it up, we have a number here. Inner product of u and v is a number. And if we have a number, we can take it outside. So we get minus inner product of u and v multiplied by inner product of u and itself, u. But u is a unit vector. Inner product of a unit vector with itself is always equal to 1. So that's just inner product of u and v minus inner product of u and v, which is the number 0. This proves that v perpendicular is orthogonal to u. And because v parallel is parallel to u, this also proves that v parallel and v perpendicular are orthogonal. A theorem about these. Some of these might be obvious to you from looking at the picture, but of course we have to prove them because if we use an unusual inner product, our picture might not really look like this one. Number one, the norm or the length of v parallel is smaller than the norm of v. Well, if it looks like the picture, that's quite obvious. The norm of v perpendicular is also smaller than the norm of v. And rule number 3, v parallel is the unique vector, which is parallel to u and is closest to v. There's a typo here. This word should be closest. Let's prove these. 1 and 2 are straightforward. 1 and 2 come straight away from the Pythagorean principle. V is equal to v parallel plus v perpendicular. V parallel and v perpendicular are orthogonal. So norm of v squared is equal to norm of v parallel squared plus norm of v perpendicular squared. So straight away we can see that rules 1 and 2 are true. Norm of v parallel must be smaller than or less than or equal to the norm of v, and the norm of v perpendicular must be less than or equal to the norm of v. So that just leaves us part 3 to prove. We need to show that amongst all of the vectors which are parallel to u, so amongst all of the vectors which look like some number alpha multiplied by u, the one which is closest to v is the one that we are calling v parallel. So what we're going to do is we're going to look at the distance between v and alpha u, actually distance squared, just because it's going to be easier for our calculation to square it. And then we want to make this number as small as possible. which vector is closest to V, which vector makes this number as small as possible, which vector minimizes this number. Now, V is V parallel plus V perpendicular. So I can write it as this. V perpendicular plus V parallel minus alpha U. Why have I written it like this? Well, because in the bracket, I have the vectors which are parallel to U, and then the one which I'm underlining in orange now is the vector which is orthogonal to U. We use Pythagoras. That's norm of V perpendicular squared plus, it would be norm of V parallel minus alpha U squared, but because U is a unit vector, we can just remove the U and have absolute value of inner product of U and V minus alpha squared. We want to make this number as small as we possibly can. The first one we can't change. V perpendicular, that's fixed. We can't change that. So the way we can make this number as small as possible is to make the second number as small as possible. The smallest that we can make the second number is by making it 0. The smallest that we can possibly make this is by choosing alpha equal to inner product of U and V. So that proves that V parallel, which is defined to be the inner product of U and V multiplied by U, is the unique vector which is both parallel to U and closest to V. Okay. The next theorem is a very, very important one. As you study mathematics, there's a few theorems which pop up which are very, very important. In calculus, we had the fundamental theorem of calculus. That's the most important theorem of calculus. This theorem is on the same level. It's one of the really, really important ones. This one is called the Koshi-Schwartz inequality. And this one says, if U and V are vectors in an inner product space V, then the absolute value of the inner product of U and V is less than or equal to the norm of U multiplied by the norm of V. And this might not look that impressive to you the first time that you see this, but this comes up many, many times in some parts of mathematics. This is used many, many times. So just like the fundamental theorem of calculus is used all through calculus in lots of mathematics, this theorem is one of the important ones which is used many, many times. And this very, very important theorem I'm going to prove. What do I want to prove? I want to prove the formula that's in the yellow box. I want to prove that the absolute value of the inner product of U and V is less than or equal to norm of U, norm of V for any two vectors in an inner product space. And I'm going to do this in steps. First, I'm going to do U equal to the 0 vector. Then we have 0 on the left and 0 on the right. 0 is less than or equal to 0. So the Cauchy-Schwarz inequality is true if U is equal to 0. And so, of course, it's also true if V is equal to 0. Next, we need to prove that it's true if we do not have 0 vectors. Before we go to any vectors, let's look at a unit vector U. Let's suppose U is a unit vector and V can be any vector, and I'm going to write V as two parts. V parallel, which points in the same direction as U, and V perpendicular, which is orthogonal to U. And remember, we have the formula that V parallel is inner product of U and V multiplied by U. Let me also remind you that if C is any scalar, the norm of CU is equal to the absolute value of C multiplied by the norm of U. Okay, so the norm of V parallel, that means the norm of the inner product of U and V multiplied by U. Inner product of U and V is just a number. If we have a number, we can take this outside of the norm as long as we put absolute values on it. So that's equal to the absolute value of the inner product of U and V multiplied by the norm of U. But wait a minute, U is a unit vector, so norm of U is just 1. So that's just the absolute value of the inner product of U and V. Previous theorem, we saw that the norm of V parallel is smaller than the norm of V. So that proves that the absolute value of the inner product of U and V is less than or equal to the norm of V. If U is a unit vector, then we've proved the Cauchy-Schwartz inequality. We've proved that if U is the zero vector, we've proved that if U is the unit vector. Now we need to do all of the other possible vectors U. So now let's let U be any non-zero vector. And then I'm going to define a unit vector called U hat to be U divided by the norm of U. I'm just normalizing U, just like we were doing in Mathematics 2. I want a unit vector which points in the same direction as U, so I just take U and I divide it by its norm. So then we have three things. U hat is a unit vector. U is equal to the norm of U multiplied by U hat. And because U hat is a unit vector, in orange, we know that the Cauchy-Schwartz inequality is true for U hat. Now I want to prove that the Cauchy-Schwartz inequality is true for U and V. We have that the absolute value of the inner product of U and V, that's absolute value of inner product of norm of U hat, comma V. Norm of U is just a number. We can take a number outside of an inner product, and then actually it's just a positive number. Positive number we can take outside of the absolute value. Norm of U multiplied by absolute value of the inner product of U hat and V. But we have a formula in orange for this. That's smaller than V. So our thing is just smaller than norm of U, norm of V. And then we've finished. That proves this very important theorem called the Cauchy-Schwartz inequality. I have a few more slides before I'm ready to take a break, because I want to prove one more theorem. We can use the Cauchy-Schwartz inequality, that's the formula in the yellow box, to prove the triangle inequality. Another one which seems obvious to us, the shortest distance between 2 points is a straight line, or in terms of vectors, the norm of U plus V is less than or equal to the norm of U plus norm of V. I've drawn the picture like this, but it depends on which inner product we're using. We might have some unusual picture. We're going to prove this using Cauchy-Schwartz inequality, and I'm color coding this. Cauchy-Schwartz I've written in green. We're going to be using it down here on this green less than or equal to. So I want to start with the norm of U plus V squared. Why squared? Because when you're dealing with inner products, it's easier to square it. I'm actually going to show that the norm of U plus V squared is less than or equal to the norm of U plus the norm of V all squared. And if I can prove that, then I have the triangle inequality that I want. So what do we do? So we have a plus in the first position. We can cut it into two just here. And then we have pluses in the second position, cut just there, simplify it, and we get norm of U squared plus 2 times the inner product of U and V plus norm of V squared. we're just taking aside, this is for real vector spaces. If we had to do this for complex vector spaces, it's a little bit more complicated here. Just a little extra things to take care of. We won't worry about that for us because we're just doing real vector spaces today. Now, how can we make this bigger? First term, that's a positive number. Third term is a positive number. And in the middle, we have a number which might be positive or it might be negative. If we put absolute value signs around the middle term, then we get positive plus positive plus positive. That must be, it might be the same or it might be bigger. And then I'm ready to use the Cauchy-Schwartz inequality. Look at the formula in the yellow box. We just have absolute value of inner product of u and v is less than or equal to norm of u, norm of v. But to factorize this, that's just the same as norm of u plus norm of v all squared. And then we're finished. That proves the triangle inequality. And then after those proofs, I think it's time for us to take a 10-minute break. I'm going to continue at 11 minutes past 3. And let's continue. Our third and final topic for this week's lesson is orthogonal sets and orthonormal sets. A set of two or more vectors in a real inner product space is called an orthogonal set if all pairs of distinct vectors in the set are orthogonal. So that means that if we take any two vectors in our set, we must have that their inner product of u and v is the number 0. An orthogonal set in which each vector is a unit vector is called an orthonormal set. So we must have two things for an orthonormal set. First, any two different vectors must be orthogonal. So if u and v are any two different vectors, they must have 0 inner product, and every vector must be a unit vector. So the inner product of u with u must be equal to 1. For example, I'm saying that this is an orthogonal set in R3 using the Euclidean inner product, or the dot product. How can we prove this? By calculating the dot product of any two pairs. We need to do the dot product of v1 and v2. We need to do the dot product of v1 and v3. And we need to do the dot product of v2 and v3. And if we calculate all of these, we always get 0. Every pair of different vectors is orthogonal, so therefore we have an orthogonal set. Now, let me remind you, anytime we have a non-zero vector v, we can divide v by its norm to get a unit vector. How does this work? Because the norm of u, that's the norm of v divided by norm of v. 1 divided by norm of v is a number, we'll take that outside, and then effectively we just have norm of v divided by norm of v, or 1. So let's suppose we use the same three vectors in R3 that we had in the previous example, and again we're going to be using the Euclidean inner product, or the dot product. I want to construct an orthonormal set. What I can do is I can calculate the norm of each one of these vectors. The norm of v1 is 1, norm of v2 is root 2, and the norm of v3 is also root 2. Please check those. And then we can do v1 divided by norm of v1. And that's a typo. That should be 0, 1, 0. u2 should be v2 divided by the norm of v2. And u3 is going to be v3 divided by the norm of v3. We have 3 different unit vectors, and because they point in the same directions of v1, v2, and v3, these 3 unit vectors are orthogonal. So that means we have an orthonormal set. I'm going to leave it for you to check that these 3 unit vectors are still orthogonal. And I'm going to leave it for you to double check that actually they really are unit vectors. Their norms are equal to 1. Theorem. If S is an orthogonal set of non-zero vectors in an inner product space, then S is linearly independent. Orthogonal implies linear independence. And I want to prove this. How do we prove linear independence? Let me remind you. We need to start with an equation of the form k1v1 plus k2v2 plus dot 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 plus knvn equal to the 0 vector. And we must prove that the only solution of this is that all of the numbers k1, k2 up to kn are the number 0. And the way I'm going to do this is I'm going to, there's a typo here, this should be the number 0. I'm going to calculate the inner product of the 0 vector and each one of these vi's. And this should be the number 0. Now remember, we're starting with k1 v1 plus k2 v2, etc. is equal to the 0 vector. So that means the inner product of k1 v1 up to kn vn with each vi should be the number 0. We've got lots of pluses. Every time we have a plus, we can split the inner product. And then every number k we can take outside of the inner product. So this is the same as k1 v1 comma vi plus k2 inner product of v2 vi, etc. In the middle we have plus ki inner product of vi and vi plus dot dot dot, etc. Another typo here, this should be kn. But remember, we have orthogonal vectors. v1 and vi are orthogonal if I is not 1. v2 and vi are orthogonal, so that inner product is 0. All of the way up to vn, this should be, and vi are orthogonal as long as I is not n. So that their inner product must be 0. So all we're left with is the number 0 is equal to ki multiplied by the inner product of vi and vi. Vi is a non-zero vector, so this is not 0. The only way that we could have this is if ki is the number 0. This proves that each ki is the number 0, and then that proves that S is linearly independent. We'll need this fact again later. An orthogonal set is a linearly independent set. Let's talk about bases. In an inner product space, a basis consisting of orthonormal vectors is called an orthonormal basis. And a basis consisting of orthogonal vectors is called an orthogonal basis. So for example, the standard basis in Rn, this is an orthonormal basis in Rn with the Euclidean inner product because all of these vectors are orthogonal from each other and each one of these vectors is a unit vector. Next, I want to talk about an orthonormal basis for Pn. We're going to be considering the vector space of polynomials of degree less than or equal to n, and this time we're going to be using this inner product. So it's basically a dot product of the coefficients in the polynomials. I'm going to leave it for you to prove that the standard basis, that's the basis 1x, x squared, etc., is an orthonormal basis with respect to this inner product. Another example. In an earlier example, we saw that this is an orthonormal set with respect to the Euclidean inner product on R3. And by the previous theorem, remember, if we know we have orthogonal, then we also know that we have linear independence. So these are not just an orthonormal set, but it's also a linearly independent orthonormal set. But R3 is three-dimensional. That means every basis for R3 must contain 3 vectors. Every set of 3 linearly independent vectors in R3 is a basis for R3. So that means this set of U1, U2, and U3 is an orthonormal basis for R3. Let's talk about coordinates relative to an orthonormal basis. Let's do a bit of revision. What does coordinates relative to a basis mean? If we have a vector space V containing a vector U, and if we can write U as a linear, of course, we can always write U as a linear combination of the vectors in a basis for V. If we do this, then the coordinates of U relative to the basis V is these numbers, C1, C2 up to Cn. Write these as a vector. We have the coordinates of U relative to this basis. If the basis is orthogonal or orthonormal, then there's an easy way to find these coefficients. So that means there's an easy way to find the coordinates of U relative to an orthogonal basis or an orthonormal basis. And it goes like this. If S is an orthogonal basis for an inner product space V, and if U is any vector in V, then you can write this. We can write U as inner product of U and V1 divided by normal V1 squared multiplied by V1 plus inner product of U and V2 divided by normal V2 squared multiplied by V2, etc. And then after we've got that, of course, these numbers in front of V1, in front of V2 are the coordinates. Let's prove this theorem. Let U be C1 V1 plus C2 V2, etc. We need to prove that each one of these CI's is equal to the inner product of U and VI divided by the norm of VI squared. And the way that I'm going to do this is I'm going to start by calculating this bit. I'm going to start by calculating U, the inner product of U and VI. And then I'm going to prove that I get CI norm of VI squared. So, inner product of U and VI. So that's inner product of C1 V1 plus C2 V2 plus dot 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 plus Cn Vn and Vi. We can split this up into n different inner products, and then in each one we have a number C, I, which we can then take outside of the inner product. To get C1 inner product of V1 and Vi plus C2 inner product of V2 and Vi, etc. Now, one of these I've done in green and the other ones I've done in red. Why? Remember, we have an orthogonal set. That means, as long as I is not 1, V1 and Vi are orthogonal vectors. So this must be 0. Likewise, as long as I is not 2, V2 and Vi are orthogonal vectors. So this must also equal to 0. All of these red terms are equal to 0. We're going to get 0 plus 0 plus 0 plus 0 plus 0 plus Ci, norm of Vi squared plus 0 plus 0 plus 0 plus 0. But that's exactly what we want. Divide both sides by the norm of Vi squared, and we get the formula that we wanted, and we've finished the proof. So that was for orthogonal basis. What do we have for an orthonormal basis? If S is an orthonormal basis for an inner product space V, and if U is any vector in V, then we can write U is equal to inner product of U and V1 multiplied by V1 plus inner product of U and V2 multiplied by V2, etc. And this one's going to be easy to prove, but we can just use the previous theorem. The previous formula was this. But now every one of our VI's is a unit vector. So every time we have norm of VI, we can just replace that by 1. And then we finish the proof. So if we have an orthogonal basis or an orthonormal basis, then it's quite easy to find the coordinates of U relative to S. For an orthogonal basis, the coordinates look like this. Inner product of U and V1 over norm of V1 squared, and then inner product of U and V2 over norm of V2 squared, etc., etc. If we have an orthonormal basis, if all of our basis vectors are unit vectors, then it's even easier. It's just inner product of U and V1, comma, inner product of U and V2, comma, etc. For example, let V1, V2, and V3 be these vectors. I'm going to leave it for you to check this is an orthonormal basis for R3 with the Euclidean inner product. Find the coordinates of U relative to this basis if U is the vector 1, 1, 1. Well, we need the inner products of U with each one of these basis vectors. Please check that the inner product of U with V1 is 1, the inner product of U with V2 is 1 minus a fifth, and the inner product of U with V3 is 7 over 5. As soon as we know these, we know the coordinates, because it's just these numbers, 1 minus 1 fifth, 7 fifths. Next example, show that these three vectors form an orthogonal basis for R3 with the Euclidean inner product. 2, normalize each vector to find an orthonormal basis. We're going to take each vector and we're going to divide it by its norm. That means normalize. And then part 3, find the coordinates of U relative to the basis S, that's the orthonormal basis S, if U is the vector 1, 2, 4. So, step 1, show that these vectors form an orthogonal basis. Actually, I'm going to leave it for you to do. I'm going to leave it for you to check that if we take any two of these vectors and we calculate that inner product, we get the number 0. This proves that this is an orthogonal set. But every orthogonal set of non-zero vectors is also a linearly independent set. And if we have a linearly independent set of 3 vectors in a 3-dimensional vector space, then we must also have a basis. So that's part 1 finished. Part 2 was normalize each vector to create an orthonormal basis. Take each vector and divide it by its norm. You can check this for me. And then step 3 was find the coordinates of 1, 2, 4. To do that, we need the inner product of U and V1. I've written V1 at the top now. Inner product of U and V2. I've written V2 at the top. Inner product of U and V3. That's at the top. Check, we get 2, 5 over root 2, 3 over root 2. And then we're finished. The coordinates for U relative to our orthonormal basis S are 2, 5 over root 2, 3 over root 2. And that brings us to the final idea, final concept for today's lesson. Orthogonal projections. If W is a finite dimensional subspace of an inner product space V, then every vector U in V can be expressed in exactly one way as U equal to W parallel plus W perpendicular, where W parallel is in W and W perpendicular is in W, the orthogonal complement of W. Now that's the notation that's consistent with what I've been using earlier, but there's another way to write these. For W parallel, we could also write this as the projection, the orthogonal projection of U onto W. And for W perpendicular, we could also call this the orthogonal projection of U onto the orthogonal complement of W. So what does this mean in terms of pictures? Let me try to show it. W is a subspace of the vector space V, and we have some vector U. The theorem says we can write this as a vector in W plus a vector in the orthogonal complement of W. And I've drawn this right angle here. In my mind, this is 90 degrees, but of course, it depends on which inner product you use. If you're using an unusual inner product, then it's not really going to be 90 degrees here. And if we combine the ideas from earlier, final theorem, final idea, final slide of today's lesson. Let W be a finite dimensional subspace of an inner product space V. If we have an orthogonal basis for W, and if U is any vector in V, then the orthogonal projection of U onto W can be written like this. And if instead we have an orthonormal basis for W, and U is any vector in V, then the orthogonal projection of U onto W can be written like this. And that is the end of this week's lesson. 2 lessons left. Next week, we're going to talk about the Gram-Schmidt process, orthogonal matrices, and then we're going to do a more complicated type of diagonalization. We've done diagonalization already, but now we're going to do the more difficult or more complicated type called orthogonal diagonalization. And then in the final week of term, we'll talk about A transpose A and singular value decomposition. Are there any questions?